Okay, let me show you how to do the ray diagrams for lenses. So you have a focal point on both sides of the lens, and then you have twice the focal length on both sides. So in this case, focal length is 50. So we're going to start off with an object that's out here. So it's beyond twice the focal length. Now the rules for lenses are lines that are parallel to the axis of the lens go through the lens and then go through the focal point. And you got to make sure you draw these things long enough. Secondly, the point that goes to the focal point on this side of the lens goes straight to the lens, and it goes parallel to the lens. And the intersection of these two rays give you the position of the image. So you get that. So this is the object. This is the image. So what you can see is that the image is smaller than the object. It's also inverted. It's upside down. And if it's beyond twice the focal length, then the image is between the focal length and twice the focal length. This is an example of a camera. Normally your object is further away and your image is closer to your focal length. Not exactly equal focal length, so that'll make it smaller. So you have your film camera. So that's the first scenario. The second scenario is you have the object between twice the focal length and the focal length. So we draw a line from the tip of the object parallel to the axis of the lens. Then it goes through the focal point on the second side. Now here it goes to the focal point and then straight to the lens and then goes parallel to the lens. And then we have a point of intersection of those two. And that's out here. And you can see that so let's label them. This is the object. This is the image. So again, the image is inverted relative to the object. The actual image is further than twice the focal length. This is an example of a projector of some sort. But it uses the same rules. Parallel on one side, through the focal point on the other side. Through the focal point one side, parallel on the other side. The intersection of the two lines gives you the location of the tip of the object. Now, the third case is this where you have an image or an object that's between the focal length and the lens. So if you follow the same rules, go to the tip, from the tip to the lens, through the focal point, you get that ray. The problem is the second one, now the focal length is actually on the left-hand side. So if we drew a point here through the focal point, it would go like that, and then it would go parallel to the lens, and you see these don't converge. So we don't have an image on this right-hand side in that situation. So we have to project backwards. So the way you project backwards is instead of going parallel this way, you go parallel the other way, like that. Instead of going through the focal length on this side, you just continue this line. And you see they both intersect there. And so that point of intersection, which is on the same side as the object, is the image. So this is the image. This is the object. So this is a case of a magnifying glass. Now, on here you're going to view the image on the screen. Likewise, the first case, you view this on the screen or on a film if you're talking about a camera. Here, you're going to be on this side of the lens, just like you were in the other cases. You're on the right-hand side. So what you see is a virtual image, since they're on the same side for the lens, and it's going to be magnified. So it's further away, but it's taller, and it's taller enough, if you think about person looking here, they have their eye close to the lens, they're going to see this angle of view for the object if they didn't have the lens, and they're going to have this angle for the image, and so the image is going to be bigger. It's also going to be further away, far enough away that you can focus on it. So those are the three cases for a lens as far as drawing the ray diagrams. Now the equation which predicts all this stuff is you get 1 over P plus 1 over Q is equal to 1 over F. It's the same as the equation for a mirror, except P is positive. In this case, P is positive when on left-hand side of a lens, and Q is positive when on right-hand side of lens. Now, in this case, well, P, what is P? P is the object distance. It's the distance from the lens to the object. So this would be P. Q is the image distance. And in this case, Q is negative because Q is the image is on the left-hand side. But here, Q is positive. It's on the right-hand side. And F is the focal length, which is on both sides, so F is always positive. And typically that's given in the problem. So let's just look at each of these cases. I'll make up a number. Object is more than twice the focal length, so this is the first example. So I've chosen 125 millimeters. The focal length is 50. So we have 1 over 125 minus 1 over Q, which is what we're trying to figure out. What is the distance to the image? Equals 1 over 50. So I'm going to have mercy on you guys, and you can just use a calculator. So what you'll end up with is, and actually it's plus, not minus. So yeah, I worked this problem out one time. I got there, used the wrong numbers. Okay, so we get 1 over Q is 1/50th minus 1/125th. So if you plug that in your calculator, 1 divided by 50 minus 1 divided by 125, you'll get 0.012. And if you had repeating digits, just leave it in your calculator. And then what you would do is you'd say Q is equal to that number, your answer, raised to the -1 power. So basically taking the reciprocal. So I end up with, if you take 1/50th minus 1/125th, you get 0.012 in your calculator. Then use a little up arrow key, left parenthesis, -1, right parenthesis, and I get 83.3. And they're the same units as the original units, which are millimeters. And so you can see right here, this is the location. So it's saying this distance is 83.3. If this distance here is 125. So that's how the equation works. So let's do the second case. Now, here let's say that the object is 80 millimeters. Focal length is still 50 millimeters. So we get 1 over 80 plus 1 over Q is 1 over 50, or 1 over Q is 1/50th minus 1/80th. And if you stick that in your calculator, 1/50th minus 1/80th, you get 0.0075. So take the inverse of that, reciprocal, raise it to the -1 power, and you get 133.3. So that's the image distance here, 133.3, for an object distance of 80 millimeters. Now the last case, the object distance, let's say, is 40 millimeters, and Q is 50 millimeters. No, focal distance is 50. So if you plug that in, you'll get 1 over 40 plus 1 over Q is 1 over 50. So you get 1 over Q is equal to 1/50th minus 1/40th, which is going to give you a negative number. So 1/50th minus 1/40th is negative 0.005. And if you raise this to the -1 power, you'll get negative 200. So now the reason this one is this really is probably close to 35, that's why. But you can see as you get closer to the focal point, closer to 50, this thing is going to move back, but it's going to be much bigger too. So when you get a negative number, that means that the image is on the same side as the object. Now there's another relationship that I want you to be able to use, and that's the magnification. So the magnification equation relates to the height. So if I have the height of the image over the height of the object, it's equal to negative, and I think it's Q over P, or the height of the image is negative Q over P times the height of the object. So let's go back to each one of these examples and talk about the magnification. So the height of the image is negative the height of the object times Q over P. So let's make the height of the image, or the object here, 5 millimeters. So that means the height of the image, based on this, it should be shorter if I did this correctly. So you have the height of the object, which is 5 millimeters. Q is 83.3, and P is 125. So you can see that ratio of 83.3 to 125 is less than 1. And so we get negative 3.33 millimeters. Now, what is the negative sign? Negative means inverted. So you can tell from the equations whether it's upright or inverted. So that negative, that's why we have the negative. Okay, so let's look at the next equation. Let's look at the next problem. Our projector. So height of the image is negative height of the object times Q over P. Height of the object is, we'll still make it 5 millimeters. But we expect the height of the object to be bigger because it's a projector. So Q is 133.3 and P was 80. So you can see that ratio is greater than 1, so it is going to be bigger. So 5 times 133.3 times 80, divided by 80, sorry. 133.3 divided by 80, and we get negative 8.33 millimeters. And so 8 is bigger than 5, so it is bigger, and it's inverted. Now the last example is this one. So the height of the image is negative the height of the object times q over p. So we have negative, let's say it's 5 millimeters again, same object, times q, which is negative 200, divided by p, which is 40. So the height of the image, the negatives cancel out, and so you get 200 times 5 divided by 40. It's 25 millimeters. And so we were talking about that today, about how you perceive this to be close and large. Well, you just see it bigger. You don't really know what it is because you don't have anything for perspective. But to us it appears larger, and it also appears further away. So if you put your eye like here, and you're looking at this image as it comes through, then it appears to be larger than this one. Even though it's further away, it still has a larger angle, relatively speaking.